Okay, so the next speaker is Ittoop Puthoor from Glasgow on analysis of quantum error correcting code using process calculus. Thanks.
Good morning. I'm here to talk about the analysis of quantum error correcting code using quantum process calculus, a work jointly carried out by University of Warwick and University of Glasgow. University of Warwick, namely Timothy Davidson and Dr. Rajagopal Nagarajan, and Dr. Simon Gay and myself from University of Glasgow. So basically the outline of my talk would begin with to explain quantum process calculus using quantum error correction code, and then the concept of behavioral equivalence, where we prove that the quantum error correction code system is equivalent to a specification process. And to understand the equivalence, we need the label transition systems and the concept of mixed configuration, and the more important property, which is a property of the congruence property, where the equivalence is valid in all contexts. And finally, we come to the conclusion. So, process calculus, to start, process calculus is a diverse family of related approaches which is used for formally modeling classical concurrent systems. So basically, process calculus includes a specification, which is a language for the precise definition of a system, and we have the semantics to describe the behavior of a system, and then we have the concept of the behavioral equivalence, which helps us to analyze the system. So process calculus has been a very successful approach in formally modeling classical systems. So extending the process calculus to the quantum versions or to the quantum systems, we have the quantum process calculus. And analyzing the behavior of systems, which comprises with a combination of both classical and quantum information, is very interesting. And therefore, quantum process calculi that has been developed till date are the three, which is QPALG, which is the quantum process algebra, the CQP, the communicating quantum process, and QCCS. So with the same motivation as that for the classical process calculus, Simon and Nagarajan developed a communicating quantum processes, CQP, which is a quantum process calculus which is based on the classical pi calculus with some extra rules for the quantum information. So CQP is a language which is defined for modeling systems which combine both quantum and classical systems. It has a formal syntax, operational semantics, and a type system. So coming into the problem, we consider here is a quantum error correction code, and as we see is a circuit model. And this is a 3-qubit flip code, and here what we devise is we put it into a 3 process, which is Alice, Noise, and Bob. And where Alice does the receiving of the qubit, which is in a single qubit state, and then does the encoding into a 3-qubit, and the noise over here flips the qubit. So it can be either a first qubit flip, or second or third, or no flip at all, and sends the qubit to Bob. Bob, on the other hand, determines whether there is a qubit flip, or understands or determines the error, and then does the correction, and after that decodes it to the single qubit state, to the original. So if this code, this code cannot correct if there are 2 or more qubits which is flipped. So if you look into the block diagram, with the help of with the semantics of CQP, we define that the quantum error correction code system as QECC, a system which has parameterized by the channels A and D of type qubit, which is given in the brackets A and D, and of type qubits, and is nothing but a parallel composition of the 3 process, which is Alice, Noise, and Bob, parameterized by their respective channels in the brackets. And this system is equivalent to its identities, or the specification process, which is a process identity which receives a qubit through the channel A, which is designated as A question mark X qubit, which means that it receives, and sends it out to the channel D, which is D exclamation X, which the qubit is sent out to the channel D. So if you look into each processes in detail, we have the process Alice. So Alice, in the sense, have parameterized by the channels A and B. A is a channel which receives, or which is the input channel which receives the qubit, and B is the output channel. And Alice also possesses 2 qubits, which is y and z, which is in the initial state of get 0, and and does some mathematical operation which is designated as in the curly brackets, which is the C0, xz star C0 and xy star C0. So a single qubit is encoded to a 3 qubit and its output through the channel B, which is xyz, and yeah, the qubit is xyz. So then noise receives the qubit from Alice, which is through the channel B, and here we can split this noise. I mean, the noise process is a parallel composition of two sub-processes, which is noise R&D and noise ERR. Noise R&D, on the other hand, the process, what it does is, with the qubits which it possesses, which is U and V, it does a Hadamard transformation, and basically noise R&D just generates 2 bits or random bits, which has values 0 or 1. And depending on these 2 bits are sent to another process, noise ERR, and depending on the values of these 2 bits, the flip is done, the error is caused. So if it is 0 and 0, if J and K is both zeros, there is no bit flip. If it is 0, 1, the first qubit is flipped. If it is 1, 0 and second, 1, 1 is third, and it goes. Yeah. So the bit flip is done with the mathematical operation, which is with the help of the poly X gate, which is shown again in the curly brackets. And the dots sign simplifies that this is a sequence of operation. So, and the dash sign, this line represents the parallel composition. So if we, sorry?
Are you only modeling spin flips or also phase flips?
This is for bit flips, qubit flip. Yeah, only qubit flip. So we have the next, after with the error where Bob receives the qubit through the channel C, and again, as similar to the noise process, the process Bob is split into 2 sub-processes, Bob rec and Bob core. And we have Bob rec also has possesses 2 qubits S and T, and receiving it from the noise process, and then Bob does the series of mathematical operations on the qubits to determine whether there is an error present or not. And based on those values of the qubits which he possesses, S and T, does a measurement and sends those values to Bob core. Bob core, a sub-process Bob core, then depending on that, if it's a first qubit flip, the X star is again flipped it back to the original state. And then after that we have the decoding process, which is xy star C0 and xz star C0, and we get it back to the single qubit original state. So Bob as such is a process which is a parallel composition of Bob rec and Bob core. So considering the execution of this whole system, which is the quantum recursion code system, here this system, the execution does not depend not only on the process but also depends upon the quantum state. So we have this is the main reason for the important reason where the operational semantics of CQP is defined in terms of process configuration, where process configuration includes, we have the quantum store, which is, and then we have the list of qubit names, and we have the process P. So in addition to the process term, the quantum state is also a determining factor for this behavior of quantum process. So hence we have this process configuration. So the quantum store is nothing but it maps the qubit names to a global quantum state. We know that the process can be subdivided into 2 sub-processes, but the state, when a quantum state which is entangled, it remains entangled, it can't split. So that's why it's a global quantum state. So initially in the whole execution of the system, we have the process configuration as nil-nil, and the system, which is a process which is nothing but a parallel composition of Alice, noise and Bob. So the semantics of CQP defines or specifies transitions between configurations, and each transition can be a communication or it can be a operation of the quantum state, which is a mathematical operation or so on. So we can say that after let's say after a set of operations which is qubits, which each process which they possess has been created, we have a global quantum state to be as a ket vector of 6 zeros, which is y, z, u, v, s, t, which is the qubits which is mapped to this quantum state. And this is a list of qubit names, and we have the process Alice prime parallel composition to noise prime and Bob prime. But this is a little different because the qubits which Alice possesses, y and z, has been created. So now Alice receives a qubit through which is the qubit which receives alpha ket 0 plus beta ket 1 through the transition is A input X. So, and after a sequence of operations of Alice, which is encoding it to the 3 qubit state, or we represent what is nothing but tau transition, means that this is internal transitions which happens within the system, which is not observable, whereas A, which was input, is an observable action which came from the environment or outside. Yeah. So the single qubit is encoded to a 3 qubit state, which is 000 and 111, and then we have the process to be outputting from the channel B to the noise prime and Bob prime. And noise prime is nothing but a parallel composition of process noise ERR and noise RND prime. So we have seen that the noise RND gives a measurement, and here the measurement gives rise to a mixed configuration, and because the results are communicated internally to the sub-processes. And the concept of mixed configuration is like to the idea of the mixed state. But the point here is that there is a correlation between the quantum state and the process. Hence we say it's a mixed configuration. So a mixed configuration is denoted as a circle with a plus sign with values j and k having 0 and 1 with amplitude of 1 by 4. And this is a quantum state, and then we have qubit names, and lambda jk here doesn't represent a lambda calculus function, but rather it shows that this is a mixed, the components of this mixed configuration has the same structure but differ in their values of j and k. And j and k are values which is at the end of the process configuration, which is where we can say that the abstracted variables x, y, z can be instantiated, which shows here. So after a set of other tau transitions, we have the mixed we can write explicitly the mixed configuration as these 4 configurations, where this represents that there's no error present, where this configuration shows that there's a 3rd qubit flip, this one a 2nd qubit flip, and this one the 1st qubit flip. Then we have the sequence of operations of Bob prime, and finally after the sequence of operations of the process Bob prime, we get this final mixed state where we prove that we find that the reduced density matrix of X when its output is the same as the reduced original density matrix of X. Now, how to specify the correctness of this whole system, quantum recursion code system? So we recall from our definition that this quantum recursion code system receives a qubit through the channel A in the state side, through the channel, and then sends it to the in an identical state through the channel D. So this is nothing but equivalent to its a specification process, which we define as identity, which receives through channel A and then outputs it through the channel D, which is nothing but this whole is nothing but the process-oriented specification. So our correctness requirement is that quantum recursion code system is equivalent to the identity process. But now for this we need a theory that defines this relation and to prove it. So here we come to the concept of the relation of which is called the behavioral equivalence. That is, if P is equivalent to Q, means that P can do the same actions as the process Q can do. So in other words, P and Q have the same behavior, or they are indistinguishable. So there are many variations for this theory of behavioral equivalence that have been developed for classical process calculus since 1980s. But our main interest is that the congruence properties, which means P and Q is equivalent, then C of P and is congruent of P, is equivalent to C of Q, means that this equivalence holds good for all process contexts, and this supports equational reasoning. So to understand the concept of behavioral equivalence to consider, we must be able to describe the behavior of a process configuration, and for that the semantics of process expressions are defined in terms of the label transition rules. We have the first transition. We can see that this is an output transition where the process here sends out the parameter 2 through the channel C, and we get this configuration. And this is nothing but an input transition where we have another process Q which receives the input, and this is V over X, means that the variable X is substituted by the value V. So if we have these two processes, parallel or parallel composition of these two processes interacting with each other, we have a single step for the system, which is nothing but C when it outputs 2 through the channel P, through the channel C, the parameter 2 output through the channel C, received by the process Q through the channel C, which is nothing but an internal action which is represented as tau. So if we see that transition 1 input is possible and transition 2 output, transition 1 output is possible, transition 2 input is possible, the hypothesis, we conclude that this single step is also possible. And moving on to the label transition, the label transition rules thus gives us a directed graph, which is a label transition system, and here the vertices are nothing but the process configurations and the edges are labeled with actions. And basically we have two types of actions, which is observable and non-observable. Observable can be input actions, which is represented as an input through the channel C, which is C question mark X, and an output action, which is C exclamation mark X. And the internal actions, which is non-observable, which happens within the system, and that's represented as tau. And coming to the concept of the notion of bisimulation equivalence, which is based upon the concept of a simulation from due to Milner, where if P and Q are able to simulate each other, we have simulation, but bisimulation requires that the simulation relation has to be symmetric. And there are three main parts and three main types, which is strong, weak, and probabilistic branching bisimulation. Strong bisimulation requires that if P can do an action alpha and comes P prime, and Q can do alpha and comes Q prime, P and Q, if they're equivalent, then we have that we can it's proved that P prime and Q prime are also equivalent. That's strong. And weak, on the other hand, is P and Q are if they're equivalent, and P does alpha to come P prime, and Q does some internal tau transitions to come Q prime, and then does an alpha output transition to become Q double prime. We can, if P and Q are equivalent, we get that P prime and Q double prime are also equivalent, and this is called weak bisimulation. So weak bisimulation allows that one tau to be matched of a sequence of 0 or more tau. But on the other hand, strong requires a tau to be matched by exactly 1 tau. But our theory here is that we use a branching bisimulation, which is stronger than weak bisimulation, and which is similar to weak. But the thing is that if P and Q are equivalent, we have also P and Q prime are also equivalent, and then P prime and Q double prime are equivalent. Taking into the probabilistic behavior arising, which is from the quantum measurements, we have the probabilistic branching by simulation. So we use probabilistic branching by simulation, and in our problem, or in our quantum recursion code system, if identity does an input, comes to ID prime, and then output to ID double prime, we have the quantum recursion code system. So we prove that this is an equivalent, and this does an input and comes to a state QC prime, quantum recursion code system, takes in the input of qubit X and comes to QC prime, then there's a series of tau transitions which happens internally, comes to a state QC double prime, and then outputs it to the qubit, and it comes to QC triple prime. We have this is a set of equivalence class 1, and this ID prime and QC prime are equivalent, and ID prime and QC double prime are equivalent to a set of equivalence class 2, and this is a finite equivalence class set. So the main part of this is that to get a congruence relation is an important task, and obtaining a congruence relation in a CQ or in a quantum process calculus is a very important task. And Tim Davidson, in his PhD thesis, has proved that the probabilistic branching by simulation for CQP is a congruence, and this requires some careful treatment for the measurement and output. The fact is, the measurement of a qubit produces a mixed quantum state, but if the measurement is the measurement of the result is outputted, then we have a probabilistic configuration, and it's a probability distribution over pure states, and then it reduces probabilistically. So we can show here that the quantum recursion code system is equivalent to the identity process, and since this equivalence is a congruence, the equivalence is valid in all contexts. And it seems the correctness of the error correction code system is a standard, But this formulation gives rise to a valuable new perspective. And to give a brief description of a mixed configuration and congruence, a mixed quantum state is a probability distribution over a pure quantum state representing some classical uncertainty. So we introduced a mixed CQP configuration, which is distinct from the probabilistic configuration. But here the mixed configuration, or when we have this measurement, this produces the mixed configuration. But only thing is that this measurement is result is not output. But if it is output, then we get is nothing but a probabilistic configuration. But since there's an internal communication of measurement which happens, we cannot remove the mixedness. But in our model, if we see the quantum recursion model, there are no probabilistic configuration because the measurement which happen is never given to the output, but it's communicated internally. So the other related work which is carried out in quantum process calculus is like, or the other quantum process calculi which has been proposed is QECC, quantum process algebra by Yoren and Lalaya group, and then we have the QCCL by Nijmegen group. But QPLG, there has not been much recent progress or in QPLG, but there has been progress in QCCS and CQP, which we were. So there are equivalence relations for both the process calculi, but the congruence relation in QCCS have been solved recently. And to conclude, so what we have seen is nothing, the use of process calculus, CQP, and its theory of behavioral equivalence. And we have seen how it's the analysis of quantum recursion code using CQP. And we've also seen that the congruence property of behavioral equivalence guarantees that the equivalence remains, or the equivalence of the processes remain equivalent in any context, and it supports equational reasoning. For instance, like Tim thesis, where he proves that the probabilistic branching by simulation is a congruence, he uses quantum teleportation as an application and also super dense coding. So in quantum teleportation is equivalent to a specification process, where that specification process is the same specification process which we see here for the quantum recursion code system. So if quantum teleportation is equivalent to the specification process, and by all means that even our quantum recursion code is also equivalent to the quantum teleportation, which is for the congruence according to the property of congruence, which hence supports equational reasoning. So to make our the future work is like, now to make this reasoning more easier and practical, we need to equational axiomatization of the equivalence, and also, if possible, also to do some automated equivalence checking. Yeah, that's all. Thank you.
Questions, comments, please. Yeah, please.
So when you have mixed states, there's not a unique convex combination of pure states that maps to each mixed state. How does that idea manifest itself in this framework?
When we in the mixed state, I haven't explained about the concept of mixed state and congruence in detail, but if a mixed configuration, we consider here as a mixed configuration, means that it's just not only the mixed state, but there's also a correlation between the mixed state and the process. Hence, we have the concept of the mixed configuration, and our transition rules or semantics are based on the configuration. So we have the mixed configuration.
Yeah.
So in your configuration, you have this quantum memory part configuration.
Sorry?
The configuration contains this quantum register. Right?
Yeah.
Do you ever reduce the size of this by hiding anything like this? Or does it just get bigger and more process issue?
In this case, we'll just get bigger.
Yeah.
Okay, I have a question. So, it's about your notion of bisimilarity. So, is it like, so can you think of some notion of equivalence that is up to unitary transformation? like so you know like if one so like there are two processes and one process does unnecessary unitary transformation that will be reversed eventually later. So such a equivalence notion, like can you think of it? Like it's not the case in your notion now, right?
Yeah.
Right, so the bisimulation equivalence, it's all based on what is input and output. Okay, so
Right.
two processes that always produce the same outputs given the same inputs will be equivalent. So if one of them internally is doing some kind of transformation and then reversing it later, then that's all included. So
Okay.
it is just the input output behavior that's.
And then this input like the communicated information that can be classical but also can be quantum, so
Yes.
a qubit can be fast.
Yes.
Okay, nice. So, yeah.
So I have a question about the mixed configuration. So maybe be more precise. So if you consider the process which is creating a qubit with probability 1/2 in state 0, and with probability 1/2 in state 1, which sends this qubit to something, to somebody, and the same process but which is preparing the state plus and minus, can you prove that these two processes are equivalent? Because the density matrices of these two quantum states are the same, so we expect that the two processes are equivalent.
Yes, I think there would be. So so technically what happens is that when you're defining bisimulation, I mean you have to have this matching between output transitions, and if the output is outputting part of the quantum state, then you look at the reduced density matrix for that state. So in the case you mentioned, if the reduced density matrix of what your output will be the same, therefore these will be matching actually, so you will get equivalence. Yes.
Okay, so there's an announcement from the local organization now, but let's thank the speaker.
Yes, I have two small announcements. One should be served diagonally across the hall here, and the second one is I saw some people coming in late. Please register with bus and buses that are here in the bush. Thank you very much. Have a nice one. See you at 2 o'clock.